Alright, I'm gonna do these ones without the camera and starting from number of islands in the graph parts. So let's go. Given an m times n 2D binary grid, which represents a map of ones, land, and zeros, water, return the number of islands. Oh, I think I've seen this problem before on somebody else's stream, but I don't remember. Or maybe even in Cold Wars, but I don't really remember. I think I didn't try to solve it. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all four edges of the grid are all surrounded by water. Turn the number of islands. So the number of eyes that are not, number of ones that are not connected, choose zeros, I assume. Is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. Yeah, so diagonal doesn't count. May assume all four edges of the grid are surrounded by water. May assume all four edges of the grid are all surrounded by water. So let me think. So I need to find a way to check if all of the adjacent, or actually not all, but oh yeah, all the adjacent are zeros. To define the boundary, I think. No, maybe not, because of the ones in the edge there. They have only two adjacent zeros. So if two or more adjacent zeros is an edge, I think. And the easiest way I can think, maybe I can do the rows and columns and stuff that the guy does always. Is length grid and length grid 0. Because the columns are the length of the lists. The rows are the length of the lists, and the columns are the length of each list. So now let me think. How can I check if each one... Yeah, so the first thing that comes to mind is the DFS stuff again. But the way that I would do it is probably... Also, I vaguely remember, maybe I should try to write it down. He passed C and then S, I think. For the previous problem. And then this part I don't remember. But then I remember he returned something like this. DFS C minus 1, S, and the other thing. Or DFS C plus 1, S, or DFS C, S minus 1. So pretty much checking all directions. C, S plus 1. And then yeah, it was something like this. And then at the end he did a nested for loop for I in range length rows for j in range if equals dfs ij. And this should check all the items, and then maybe there was an if statement. Probably, actually. So it was something along the lines if c lower than 0 or s lower than 0 or c greater or equal to rows or s greater equals. Because I'm passing, the first one is going to be the rows and the second one is going to be the columns. And then there was 2 other conditions, but I think the other ones were related to the other problem. And then he returned false here to stop the execution, from what I remember. So this should be the same logic for finding the squares. And then the thing that is different about this one from the other one is that the other one is trying to find the path, if I remember correctly. So maybe it is the same thing, or close to it. Because I have a set here. He made a set called path. And then he appended something to the path each time. And that's the thing that I don't remember really well. So I'm traversing in each direction. And let me think. Oh, he did something along the lines of path.add and then sc and then path.remove sc. And then maybe he didn't return here, he returned after that, after this nested calls here. These nested calls. I don't remember really well. But at least I'm happy that I could remember this much. So I definitely feel improvements now from the previous one. So the biggest thing is, how do I know what logic to put in order to determine the boundaries of the edges of each island? That's the biggest challenge here. So I think this problem can be broken down into these 2 different steps. One is traversing the grid and maintaining, using the backtracking stuff to maintain to get the path of the thing. And yeah, so what's the difference between this one and the other one? The other one is looking for words, so you have something to compare to. And this one, you're looking for the island, so it's a different sort of logic to define the space, the limits of the path, I think. That's the biggest difference. But from here, I don't know how to proceed, I think. Let me think if I can come up with something. I'm also pretty sure that I'm forgetting something from the previous problem, but and it was probably something related to the path, but I forgot exactly what it was. Oh, and here was also something like or s in path, something like that, to check if the path already exists. So let me think. And probably there is a better solution than this as well. Because I suspect, since it's graphs now, there's probably a different way to do this. So I think the difference between the graph and the tree is that the graph has connections all around, can have cycles, and the tree is just top down and bottom up. So maybe that's the logic I should be thinking about instead of this one. Should create a graph. So maybe parse the matrix into a graph, and then, yeah, probably that's the best way to solve it actually. You parse the matrix into a graph, and then use the values of the graph. You traverse through the graph to define the islands. Maybe. How would you do that? Yeah, I'm not really sure how to build graphs because the tree has the root and then left and right values, but the graph, because it doesn't have any hierarchy, then I'm not sure. I guess each node can be connected to as many nodes as possible. But in this case, it would be to the neighboring nodes. So maybe I can use this DFS to create the object of each node. I create a different class outside of this, and then I traverse through the matrix, and I put the values of the. But then how I'm gonna? Oh wow! It's actually always gonna be 4 different values. Is either gonna be left or right or up and down. So maybe I could do that actually. I can create class with graph def init. I'm not going to be able to solve it, obviously, in this amount of time, but the point is just to go over the logic and see if my line of thinking is similar to the recommended line of thinking to solve these problems. So here I would have left, right, up, down, and then value. Then self.left equals left, self.right equals right. So pretty much the same thing as the tree, but with 2 extra values. Self.down equals down, self.out equals well. And then I do this backtracking technique here, and let me see. So here I'm going through all the nodes, all the elements in this list here, in this matrix. And then I'm increasing here. So maybe instead of doing, well, I actually need to, maybe I just don't return false. Because then I probably remove this path stuff. And then here I add the logic. Let me remove this. So here I create a graph for each node. The thing is, how would I define what is up and down? Because I'm only moving in one direction at a time. So that's the problem here. So maybe I'm confusing because again, it makes more sense for me to put this inside of the recursive call. So I have the indexes, or to mix this inside of the call here as I'm traversing to the paths. So I have all directions. So maybe that's a different way to do it actually. Instead of doing this nested for loop here, I just create left, right, up, and down. And then I do this with the other statements as well. Or so if left, right, but it doesn't feel like it's gonna be that efficient. That's the only thing. Up, oops, up, down. Oh, if left is 0, so here left greater than. And then I can't use the columns and rows as well. Yeah, both left and right has to be in the rows. So if I'm moving left, then left has to be greater than 0. If I'm moving right, right has to be, right can't be the rows, so I think I'm gonna remove this. So it's like breaking down the two different directions from the previous one into 4. And then the columns, if up or, so maybe I should put the statement here, like or here, and then here, if down less than 0. And maybe this is a better way. And then here, instead of doing this, I do left, or right, no, left plus 1, right, up, down, then left, right minus 1, up, down. So the way that I'm thinking, I'm going to change each direction once. But the problem with this is that I know that it's extremely inefficient because I'm repeating the trajectories a bunch of times. But at least it's the way that I can think about it right now. So and then up plus 1, down. And then left, right, up, down, minus 1. And now that I have the 4 different directions, I can check, I can create the node based on that. And then I will need to have a, yeah, I can, then I can create another class, or maybe I can append these nodes into a list outside of this call. So I'm pretty much using this function to parse the inputs of the matrix into this graph format here, this graph object. And then I put this graph object into a list and I figure out a logic to find the boundaries between them. And I check for all the coordinates. So I'm gonna look at the solution, but that's probably the way that I would go about it if I have a lot more time. And I'm pretty happy about that, honestly, because I can feel some improvements in my thinking from the previous ones already.
LeetCode 200,
even though
number of I
failed all of the other ones. And I think the key takeaway I want to put out there from doing this list is that it's pretty much normal to be like that in anything that you do, pretty much. Initially you suck, and then you just have to accept that. And then you figure out what are our weaknesses and strengths, and then you work on that and you become good eventually.
islands. This is actually one of my favorite problems because I feel like a lot of graph problems build upon this one, and you can learn a lot from just this one problem. It's also a really popular interview question. A lot of big tech companies, including Google and Uber, ask it, so it's a good question, a common question to understand. So we're given a 2D grid where ones represent land, zeros represent water. We want to count the total number of islands that exist, right? And in this case, an island is defined as ones being connected adjacently, horizontally or vertically, not diagonally, right? So they have to be connected horizontally or vertically. And the entire grid is surrounded by water. So in this example case, we can see that there's only one island, right? This portion of ones, and they're all connected horizontally and vertically, and there's nothing else. The rest of the grid is just made up of water, so we don't have to look at it. So if you don't know how to solve the problem, the first thing you should do is not try to write any code. Just look at the picture and try to get as much information as you can. So think about it. How would a kid solve this problem if you gave them the picture and told them to count the number of islands? Well, the first thing you would do is notice, okay, let's start at the top left. Hey, there's a 1 here, right? Okay, that means it's an island. How many other ones are connected to this one horizontally and vertically? Just by looking at it, right, you kind of draw the outline. There's all these ones that are connected to each other. So then that's one island. We can say that the number of islands we have so far is 1, right? And if you look at the other ones, right, maybe we have to count those as well, like this one. But you notice it's already a part of the island that we drew, right? This outline, it's already there. We're not going to count it twice. These ones are a part of the same island. So the count of islands.
Also, another takeaway here, and something that I want to make sure I'm focusing on the most, is improving the way that I think and not necessarily figuring out how to solve those problems. And that's why sometimes on some of these problems I don't feel like doing them because it feels like a waste of time. Maybe because they are too easy, or because I feel like they're not going to improve my thinking, and that should be the main priority always, I think. So it's much more about figuring out your natural inclination to think about solutions to these problems, and then see the way that the people that know how to solve them think, how they break down the problem, and how do they come up with the best way to solve it. So pretty much their algorithm for identifying what data structure they're going to use and the steps to solve the problem in the logic, and figuring out your natural inclination to solve them, and comparing the two, and then bridging the gap between them in the way that you think. And that's the main takeaway, I think. Because the more you can do that, you can extract the cause and the first principles of any problem that you have, and then you become better at identifying these problems in real situations, and understanding, increasing your self-awareness over your tendencies and the way that it's usually the optimal way to approach whatever problem you're facing.
Remains 1. And after looking at each of these ones, we'd conclude the same thing, right? They're all a part of the same island. Next, we could look at some of these zeros, right? Okay, we check, is this an island? Nope, it's water. So just cross it out, right? Don't need to consider it anymore. Is this an island? Nope, it's water. This is water, 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 this is water. It's getting pretty repetitive, but this is water, this is still water. But now we get to a 1. That means we found another island. And it's not a part of this island that we already counted, right? It's a part of a new island. So we're going to update the number of islands. Cross 1 out, now we're going to put 2. But we have to remember that we have to count all the ones that are connected to this one. And there's only one right neighbor that it has, right? And so the total number of islands is now 2. When we get to this one again, we see it's already a part of the island that we already counted, right? So we don't have to count it again. So we visited every single cell and we concluded that the total number of islands is 2. So now we kind of have an idea of how the algorithm works. But the difficult part is that you might not know, unless you know a little bit about graph algorithms, is how do we actually determine this entire area, right? How do we get all of the adjacent neighbors of an island? How do we mark them as visited, right? Let's take a look at how we can do that. So when we first got to this one, we realized we got to an island, but then we wanted to mark the contiguous land of this island as visited, right? So the first thing we could do is say, okay, well, the adjacent neighbors of this one also have to be marked visited. So its neighbors are this one below it and this one to the right of it. Okay, but we're not done yet, right? There could be even more ones connected to these two that we just visited. And then we can say that for this one below the first one, its neighbors are this one and this one. But what about this one above it? Well, it's already visited, so we don't want to mark it twice, so we're not going to do that. Now let's get the neighbors of this one that was to the right of the original one. So it has one neighbor to the right of it. It also has a neighbor below it. But hey, we already marked that visited, so we don't need to do that again. And then let's look at this one and see its neighbors. Well, it only has one. And then we notice that this one doesn't have any neighbors that aren't already visited, and this one doesn't have any neighbors that aren't already visited either. So you might already know what this algorithm is, but it's basically a breadth first search. We're just doing a graph traversal algorithm starting at the original point over here and marking each layer of ones. So in the first layer, we got this. The second layer, we got this. The third layer, we got this. And the fourth layer, we had just a single value. So this is really easy to visualize, and if you already know this algorithm, you can code it up pretty quickly. So knowing what we just learned, let's code it up. So the first thing, just do some input validation. If we had an empty grid, we don't want to have to run our algorithm, and we can simply just return 0. There aren't any islands in that case. The next thing I like to do is just get the dimensions of the grid, so the number of rows and the number of columns. We can get the number of rows by doing this, and the number of columns by doing this. We also want to be able to mark positions or cells visited when we're marking island masses, so I'm going to use a set to do that. We could also use a 2D grid if we wanted to, but I think sets are a little easier. We also want to count the number of islands. We can initialize that as 0. So we want to visit every single...
So he does use the same logic with the path, but now he's calling visit, but it's pretty much the same thing from the previous one.
...position in the grid. So let's iterate through each row and column. So R is going to go through every single row. C is going to go through every single column. If we visit a 0, we don't have to do anything, right? But if we visit a 1, then we have to do something. Then we have to traverse it and mark it visited. And don't forget that this 2D grid is actually made up of strings, not numbers. That always trips me up. I think it's kind of annoying that LeetCode does that, but it does. So now we have to run our traversal. I'm going to run breadth first search because I kind of like it. So run breadth first search on this cell, row, column. We also have to increment the number of islands. But remember, we're only going to be incrementing the number of islands if we get to a one that we haven't already visited. So we're going to make sure that if we execute this, we've gotten to a position we haven't visited. And then ultimately, we're just going to return the number of islands. But we didn't actually write our breadth first search. Let's do that right now. So breadth first search is not a recursive algorithm, it's iterative, so we need a data structure to use for memory, so a queue is normally used for breadth first search.
I guess another thing that I have to remember is that this RC is the index of, so it's kind of the location in the matrix, and that's why he's checking to see if it's on the set. At least that's the way that I think about it, but it's a little bit confusing for me. This check here to see, the path is not that clear to me.
So we want to mark this position visited as well. So to visit, we're going to add this cell that we're about to use our traversal on, RC. We're also going to add it to our queue. And so while our queue is not empty, that means we're going to be expanding our island. So we're going to pop from the queue. And we want to check the adjacent positions of this position that we just popped. So the way I like to do that is use a loop. So we know that there's 4 directions that we can go in. The direction to the right, which is 1, 0. The direction to the left, which is -1, 0. The direction above, 0, 1. And the direction below. Now, for each of these directions, we're going to check something. First, we want to check that this position is in bounds. The way in Python I like to check that is just if r plus dr is in range of rows, and check that the column plus direction that we're moving in is also in range of columns, and that this position is a land position, so this is equal to 1, meaning it's land. And lastly, that this position hasn't already been visited. So if this is true, then we can add that to our queue because that means we have to run breadth first search on this cell as well. We also have to mark it visited so we don't visit it twice. I noticed that we're doing this computation a lot by adding row plus direction of row, so I'm going to fix that really quickly. So that's a little bit cleaner, and that's pretty much the entire breadth first search function. It's going to be running until the queue is empty, which means that there's no more land positions to visit. I had a sloppy bug. I forgot to add this row column position as a tuple, which we want to do as a pair, not 2 elements separately. I also used the wrong function name for visit. We have to use visit add, not append, because it's a set, not a list. And there is the breadth first search solution to this problem. Sorry about a few of the bugs that I had. I hope they didn't trip you up too much. And also
Again, I don't understand really well this stuff here, but I have to go to the next one. The next time, after I finish the list, I'm going to spend a lot of time on each problem. I'm still debating whether or not I'm going to put a timer on each one and just increase the time that I spend on each problem, because I don't want to make sure I don't want to spend too much time on any specific problem. So, but I'm going to focus on really trying to understand very in depth, but only after I'm done with the list. So this first part is just making sure I go through them quickly. So even though I don't remember the previous one, I want to go to this one, which obviously is going to make it a lot less likely that I maybe should solve this one, but that's not the point of doing this this time. The point is understanding the variety of problems and what's trying to identify the most common patterns. So when I go in depth into them, I know what I'm looking for, and I have in the back of my mind the stuff that I need to understand. So this comes from a book called 7 Habits of Highly Effective People. And one of the habits that he talks about is begin with the end in mind. So you should always know what you're aiming for when you're studying, and I think it's a much better way to do it. And that's why, but then there's the trade-off, obviously, because if you just stay at the superficial level, never learn, and if you go too in depth, then you lose the holistic approach, the holistic view of the patterns. So that's why I think combining both is the most powerful way to learn fast. But I could be wrong, obviously, as well. It's just the way that I think that I'm approaching this right now. Given a reference of a node in a connected and undirected graph, return a deep copy clone of the graph. Each node in the graph contains a value int and the least node of its neighbors. So I'm given a reference of a node in a connected undirected graph. Reference of a node. So I guess it's just a pointer to the node. And it's an undirected graph, which means that it doesn't matter the connection between the nodes, or like it says, it doesn't matter the direction of the connection, just the connections. So each node has a value, and the neighbors, which are the nodes. Neighbors, if not, it's not none else. Okay. So if it has neighbors, it's going to be on a list, and else it's going to be none. And you need to clone this graph. Mathematics and computer science connectivity is one of the basic concepts of graph theory. It asks for the minimum number of elements, nodes, or edges that need to be removed to separate the remaining nodes into two or more isolated subgraphs. It is closely related to the theory of network flow problems. The connectivity of a graph is an important measure of its resilience as a network. Okay, I'm not gonna read all this stuff. Each node in the graph contains a value, int, and the least nodes of its neighbors. Okay, think I got it now. Test case format. For simplicity, each node's value is the same as the node's index, one indexed. For example, the first node with val equals 1, the second node with val equals 2, and so on. The graph is represented in the test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in the graph. The given node will always be the first node with val equals 1. You must return the copy of the given node as a reference to the cloned graph. It's kind of confusing, to be honest, to understand what they're asking you to do. They want you to copy the graph, but each value, okay, so the value of the node is equal to the index, starting from 1. So this is probably a hint of something you can do. I remember seeing this in a previous problem, but I don't really remember what does it means. But I guess it's for breadth first search, if I remember correctly, or something like that. Yes, because probably you're gonna have to create another set of objects or lists, and then you're gonna have to start from 0. So because the 0 one is discarded, it ends up working out, but I don't remember really well exactly how that worked. I think it was something related to breadth first search, but I don't. Maybe it's because the last node is no or none, and then yeah, whatever. For example, the first node without 1 equals 1, the second node without 2, and so on. The graph is represented in the test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes a set of neighbors of a node in the graph. The given node will always be the first node with val equals 1. You must return the copy of the given node as a reference to the cloned graph. Always be the first node with val equals 1. Okay, so I'm giving the first node and then I need to search for the other nodes. I think I get it now. So they pretty much want you to run a search on the graph and copy all the possible nodes into another graph. So it's a search problem, I think. And you're probably going to implement either breadth first search or depth first search. And I'm not sure which one. Probably from the intuition I have now, I think it's breadth first search, because it makes more sense since the neighbors are list. But I could definitely be wrong about that, because trees can also be represented in a list, and what changes it is the index. So suppose there is one trick with the index. Oh, I think I remember now. Is the problem with the in-order traversal and pre-order traversal, where I had to use both of the lists, the one that I tried to do yesterday, and you had to combine them to find the medium or something like that. And because the index of one was different than the other, then there was something with this one indexed here, but I don't remember really well. Given node will always be the first node. You must return copy of the given node as a reference to the cloned graph. Original graph. You can return the same graph. This looks like a clone. The nodes are new. Graph looks the same. How does it know if the nodes are new? That's the thing. Maybe that's why the index is different. the nodes were cloned, but the graph is messed up. It doesn't have. So the first thing that I'm thinking about, which I think is wrong because I'm not gonna incorporate anything that I've learned before, is take the first node, then loop through the neighbors, and for each neighbor, do this recursively. So maybe call recursively on the nodes and the neighbors and store that into the other one. But I don't think that makes sense because the problem is, oh yeah, for each node you create the same object, but then I think you have to return this in a list at the end. There are 4 nodes in the graph. First node, neighbors are second, node value 2 and 4. Second node values is 1 and 3. Neighbors are... Oh, so it's gonna pass all the nodes of the network and the neighbors. So it's a list of lists, I think, that it is passing. Yeah, probably. Adjacency list. So can't I just loop through this list and make the value equal to the, and the neighbors equal to the list? It can't be that easy, so I'm probably missing something. So if you do for n in nodes, each n is gonna be a list, or for key n in nodes enumerates nodes, then the new is gonna be the nodes with the value of the key, and neighbors is gonna be n. But that doesn't make any sense. It should be this easy. And then new graph, and new appends, new graph, appends, new. So I'm definitely missing something here. Turn new graph. Because this is also not a graph as well. That's the thing. Node object's not iterable. Yeah. So they pass. That's the confusing thing, which is also the same way in trees, is that it is represented in a list, but it's actually a nested object, and that's why it's confusing. So I think this is not... so instead of, this is going to be an object with the value of 1, and the neighbors is going to be the list. And that's the thing. Because you can't go linearly from one to the other. You have to go through the sublist in order to get the other ones. And that's why it's probably breadth first search or something like that. So maybe I should try to use the queue stuff. Q equals the queue. And then I pass nodes into this while q n equals q.pop left. Each one's going to be a node, and then based on the neighbors, so n.neighbors, I should append the queue or something like that. For neighbor in n.neighbors, q.append neighbor. So I'm appending the neighbors of each node into the queue. which is gonna be and. So that's the way that I'm gonna go through all the nodes, I think. But then for each one, I need to create a new node. And this node is gonna be and dot value. Oh, but that's the thing that I'm not sure about. Because then isn't an identical copy. So maybe we should be using this deep copy here. Deep copy. And I should import this library. Then n dots neighbors not deep copy. And then I have to check if there is a neighbor or not. And int object has no attribute deep copy. And this should be, I should initialize here as well. New node equals node. And then put here, new node dot value is equal to this. Neighbors. So let's remove the deep copy and see what happens if I do just like this. And I have to check as well. So probably if and then I do this. Probably wrong, but yeah. So that's the thing. I'm not getting any no values because it's different than the tree. I'm just going through all of them. So maybe I should keep track of the ones that I visited somehow. I can append to another list. And then here, so yeah, but now how do I check? So maybe if n ends, if n ends and not in visited, maybe like this. Oh, I forgot to append. I need to append the nodes. So probably append here. But then maybe I don't need two different lists. But I think I kind of do because I'm using one of them to search and the other one to check. So makes sense, I think. Let's see if I append in the end. Or here. And maybe it should be a set instead of a list there. giving me a problem here. But I think this is gonna be repetitive, that's why I was talking about doing a set. But pretty much the logic here that I'm trying to implement is appending to the visited to check in the next iterations if I visited the node or not. And I'm using the queue to explore all the nodes, all the neighboring nodes of each node in the graph. And then for each node, I'm copying through this new node here. New node dot value equals n dot value. So it's saying that this is a list. I'm not sure. It's probably because of the copy stuff that I need to be doing at some point. But then it says maybe here, deep copy. Because on the value it was saying that I can do it in an integer, so maybe I can do it on the list. Yeah. An alternative is a deep copy meaning the fields are dereference rather than reference to objects being copied. New copy objects are created for any referenced objects and references to this placed in B. The result is different from the result a shallow copy gives in that the objects referenced by the copy B are distinct from those references by A. So maybe I should just be making n equals deep copy like this and then removing this part. There's no attribute deep copy. Oh, it's because I need to pass like this, I think. That's the problem. But this is probably better anyway. I'm gonna look at the solution now because the time ran out, but yeah, okay. So let's look at this.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem clone graph. So we're given a reference to a node that is in a connected undirected graph. So it's convenient for us that the graph is completely connected. And all we want to do is return a deep copy of that graph. In other words, a clone of that graph. And for every single node, we have two things. We are given a value, and we're also given a list of its neighbors. So this is what's telling us, how the graph happens to be connected. These are the edges in our graph. Now, if you're not super familiar with what a deep copy is, so let's say that this is our example, our input graph. We're not just going to create a shallow copy, meaning like this is the exact same graph, like the color is yellow for both of these, meaning like it's the exact same graph. We didn't actually create a clone of it. So this is not what we're looking for. This is also not what we're looking for. So this is a new graph because the color is slightly different, but you see that the values aren't exactly how they're supposed to be. We have a 3 here, whereas we have a 2 in the original graph, right? So basically we have these two's values mixed up. So that's not what we want either. We want an exact clone. So it has the exact same structure and values, right? The values and structure is the exact same. And this happens to be a new graph. This is not the exact same graph as this one because this one is blue, whereas this one is yellow. So how are we going to solve this problem? Well, you can see I'm going to use a hash map like pretty much every graph problem, and we're going to use depth first search, where you can also use breadth first search if you want, but let me show you the general algorithm. So you can see these edges are undirected, meaning, if 1 has a neighbor 2, well, 2 is also going to have a neighbor 1 in its neighbor list. So let's say that 1 is our entry point in the graph. What are we going to do? You can see initially our hash map is empty. What we're going to try to do is map the old nodes to the new nodes or the copy nodes. So we start at 1. So what's the first thing we should do? Well, obviously we should create a copy of this node. That's what I'm going to do. So create a copy of 1. Now this copy of 1 is not complete yet, right? Because take a look at the original one. It has 2 neighbors, 3 and 2. So what can I do? We know we're going to have 2 neighbors for node 1, right? Can I just take these 2 original nodes and then put them over here, 3 and 2? No, I can't do that because for these nodes 3 and 2, we actually have to create copies of them as well. So you can see that this is going to be recursive. So first thing I'm going to do is I'm going to go to its first neighbor, which let's just say it happens to be 2 in this case, right? So I'm going to start cloning starting at 2. So we're at 2, we're going to create a clone of 2. Oh, and by the way, before I forget, before we make a clone of 2, we know we just created a clone for 1. So what are we going to do? We're going to map the original node 1 to its now clone node 1. So we're mapping the old node to the new node. And I'm going to show you why we're doing that in a second. So now we're going to go to node 2, right? And we're going to create a clone of node 2. So let's create that clone node 2. We're also going to add it to our hash map, right? We're mapping the old node 2 to its clone. So the clone in blue is the new node. So now we've cloned 1 and we've cloned 2. And for 2, now let's look at 2's neighbors. Well, look, you can see that it has a neighbor of 1, right? And it has a neighbor of 4. So first, we're going to end up trying to do is create a clone for 2 because we know that we have to, in the list of neighbors for 2, we have to add the clone 1, which we haven't done yet. So what we're going to end up doing is we're going to try to clone 1, but we're going to see in our hash map, look, we already ended up cloning 1. So basically what I'm saying is now we can say, okay, we can add this edge that 2 is connected to 1, that 2 has a neighbor that happens to be 1. And basically the reason I'm doing that is because we know that this edge is going to be undirected. It goes both ways. So that's what I'm trying to do here. So now we know that 2 is connected to 1. We also know we have to clone node 4. So now we're going to visit position 4. Let's create a clone for 4. So let's add it to our hash map as well. We're mapping the original node 4 to its clone. So now we're at the node 4. We want to clone 4's neighbors. First, you see that 4 has a neighbor 2, which we already cloned. So we're going to take this original node 4, right? We know the original node 4 has an original neighbor of 2. So then we're going to take that 2, look it up in our hash map, see, okay, we already created a clone of it, and this is the clone. And then we're going to end up taking 4 and connecting it to 2. And let's just say that, when we created the node 4, we ended up connecting 2 to 4. So let's just make this edge go both ways because we know that originally the edges are undirected. So now that for 4, we wanted to create a clone of 2. We also want to create a clone of its second neighbor 3. So now let's create a clone of 3. So we know that 4 is going to be able to connect to this neighbor of 3. So we're creating a clone for it. And we're going to take the original 3 node and map it to its new copy node of 3. So now we're almost done, right? You can see that all 4 of the nodes have been copied, but for 3, we haven't added 3's neighbors, right? 3 isn't ended up connecting to any other nodes yet, but we know in the original 3 has 2 neighbors. The first neighbor is 4. So we're going to say, okay, we know that this 4 needs to have a clone, but the good thing is we already created a clone for that node, and this is the clone. So now we have it. So we're going to take 3 and connect it to 4. So we're going to make this edge basically double directed. And 3 also has another neighbor of 1. And so basically what we need to do is make a clone of that one, but we look in our hash map first and we see we all.
I'll be right back. You should go to the bathroom.
already cloned 1. This is the clone. So we're going to take 3 and connect it to 1, right? But wait, we have one last problem, right? This 1 should also be connected to the 3, right? You're right. And that's what we're doing recursively now. So we originally started at 1, then we went to 2, then we went to 4, then we went to 3. Now what we're going to end up doing is reversing that because we remember we're doing this recursively. So we're going to pop back up to 4. We're going to see 4 has already cloned its neighbors. 3 already cloned its neighbors. We're going to pop back to 2. 2 already cloned its neighbors. We're going to pop back to 1. 1, we ended up cloning the neighbor 2, right? But we didn't end up going this way. So from 3 now we're going to end up checking, okay, did we already clone 3? Let's look in our hash map. Yep, we already did. So this is the clone that we created. So all we really need to do is make 1 connected to 3. So basically make this edge double directed. So now you can see that we finally created a complete clone of the graph. We did this in O of n time, where n is basically the number of edges plus the number of vertices, right? The number of nodes plus the number of edges connecting them, because we have to basically make a clone of each of these. And with that being said, now let's jump into the code. So we remember that we only need a single data structure, old to new, which is a hash map mapping the old nodes to the new nodes. And I'm going to implement this in depth first search. And you can see that this function is nested in the outer function, which just makes things easier, meaning that this data structure doesn't need to be passed into every single function call, but we do need to pass in every time the node that we're visiting. So in depth first search, we're going to pass in the node. First thing we're going to check is if the node is in our hash map. If it is in our hash map, then that means we already made a clone of it. If we already made a clone of it, then I'm just going to return that clone. We don't need to create another clone. So if it exists, return the new node. So if this statement doesn't execute, that means a clone doesn't already exist. So let's create that clone. I guess I'll call it a copy. So we're going to create a copy of this node. So we're going to use the node constructor, and the value we're going to give it is the value of this original node. And we're also going to take that copy and then add it to our old to new hash map. So old to new. So the old node is just node, and the new node is the copy. So we're mapping the old node to the copy. And then we want to make copies of every single neighbor of the original node. So node.neighbors. Let's go through every single neighbor, and let's run depth first search on that neighbor. And so basically, if we run depth first search on that neighbor, what it's going to do is it's going to return the copy that we end up creating. And with that copy, what am I going to do? I'm going to take this old node, or this new node, the copy that we made, and I'm going to take its list of neighbors, and I'm going to append to that list of neighbors this the return statement from this depth first search call. So let's copy and paste that in here. So that's all I really need to do, depth first search, and add it to the neighbors of this copy that we just made. And once we're done making all the copies of the neighbors, then we can return the copy that we just made in the current function call. And it's actually that simple, because even though this is called depth first search, it might even be better to call this function clone, because cloning is basically what we're doing. We're taking the original node and creating a clone of that node, and we're cloning all of its neighbors recursively. That's what this recursive call is, right? And then to the neighbors that we're creating, we're adding them or appending them to the list of neighbors of this node. And so it's actually the last thing to do is easier than you would think. We're going to call depth first search, passing in the original node that we're given in the original function call, and then we're just going to return the result of that, because that's going to give us the connected graph. It doesn't really matter which node we return, I think. So any node that we end up returning is good after the entire clone has been made. Oh, and one last thing, we forgot to check one edge case. The original node that we're given could be null. So if the node is non-null, then we're going to call this function return the result. Else, if the node is null, we'll just return null. So with that being said, this function should work. And there you go. It's pretty efficient, even though this indication makes it seem like it's not. I think if I ran it one more time, it would probably be closer to like 50 or 60%. But I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
Yeah, I don't understand really well there.
See you pretty soon.
Why he doesn't return the results, or the final return doesn't involve the hash map here. But I guess I understand the logic. So it's pretty much it's very similar to the way that I was thinking, but he runs the recursive call on the neighbors and then creates the copy through the hash map instead of calling deep copy. And he's using depth first search instead of the breadth first search. It's okay. I'm gonna go to the next one. This one specific. Let me see. 43. Damn. There's still a lot to go. There is an M times N rectangular island that borders both the Pacific Ocean and Atlantic Ocean. The Pacific Ocean touches the island's left and top edges. The Atlantic Ocean touches the island's right and bottom edges. The island is partitioned into a grid of square cells. You are given an M times N integer matrix heights, where heights RC represents the height above sea level of the cell at coordinate RC. The island receives a lot of rain, and the rainwater can flow to neighboring cells directly north, south, east, and west if the neighboring cell's height is less than or equal to the current cell's height. Water can flow from any cell adjacent to an ocean into the ocean. Return a to the list of grid coordinates result, where result I equals our I CI denotes that rain water can flow from cell to both the Pacific and Atlantic Oceans. So goddamn. So each one of them is the neighboring of the matrix, is the boundaries of the oceans. What's 0, 4, 1, 3, 1, 4. So I guess it's this one, 0, 4. 1, 3 is probably this one, 1, 4. So the highlighted ones is the ones that is supposed to so they're giving you a matrix, and you need to figure out. I'm not really sure which ones exactly. Let me go back again and read the logic, read the statement to see if I can get the logic. Integer matrix where I represents the water can flow to neighboring cells directly north, south, east, and west if the neighboring cell's height is less than or equal to the current cell's height. Water can flow from any cell adjacent to an ocean into the ocean. I don't understand this part. So it's saying if it reaches the level, the number of the cell, but what does that mean? So each value of each cell represents the sea level. With the cell at coordinates above sea level. So this is above the sea. How many is above the sea? A lot of rain. The rain, so this is the island, okay? Rainwater can flow to neighboring cells directly north, south, east, and west if the neighboring cell's height is less than or equal to the current cell's height. Water can flow from any cell adjacent to an ocean into the ocean. A grid result where denotes the rainwater can flow from cell to both the Pacific and Atlantic Oceans. God damn, man. Not sure if I even understand. I guess I know what they mean, but to think about an algorithm to do that. So you pretty much need to find a cell where all the other connecting cells have a lower value until it reaches the boundaries of both oceans. And if both oceans can be reached from that cell, you need to return that cell, which is incredibly difficult. Maybe not actually, if you think about it, because if the cell level is higher than the row and column levels of the other cells, until it reaches the boundary, it means that it can go both directions. So again, I think you probably need row and columns. Rows, columns equals length, heights, length, heights 0. So for example, 5 here, if 5 is bigger than all the other elements in both directions, vertical and horizontal, it means that you should return. So you should probably traverse to this and then run depth first search again. So there's probably going to involve a nested for loop. Length rows, rj in range length calls. And then you're gonna run this like this, probably something like that. There's probably a path as well. The path thing is the one that I keep forgetting how the logic relates to the problem. So here I'm probably gonna have, see, I think it's S, the R, RS, RC actually. Should probably do like this maybe. Thread. And the thing is how I'm gonna keep track of all of the elements. Well, I guess I have the heights, the matrix. I think checking for all of the elements in the vertical and horizontal for each number is true is low. But that's the only way I can think now. So pretty much you separate into a function the vertical and horizontal for each element. And then what do you need to return from that function? So if the current elements, so maybe I should pass current here as well. Current. And then how I'm gonna know what is the current element. But then I should put if current element greater or lower than heights are C, return false. And here you run this with r-1, C, or R, C. You go in all directions, I think. It should return this. So this only returns true if the current element is greater than all the other in the vertical and the horizontal path. And I also should put another condition to say if right less than 0 or greater than rows or C 0 or C equal C return. And then I need to pass the current element here. Current equals height ij. That's current here. And then, so if this, then I append to a new list. And then I need to append the position, I think. Ij. And at the end I return this. Probably not right, but whatever. Object int has no length. So it's just rows, actually. Heights and heights. Oh yeah, I forgot to pass currents on all of them. Hmm. So am I passing them correctly here? I is rows. The first one should be rows. I'm upgrading them, rows, rows. And the other one should be the columns. So seems to be correct. So what am I missing here? If columns greater than 0, probably. Actually no, doesn't make sense. Because I'm decreasing the columns, so it should be greater than 0. It should continue, and it can't be bigger than columns when I'm upgrading. So I'm not really sure what's going on here. Maybe I'm doing something wrong in the rest of the logic because I'm reaching the max depth of recursion. Maximum recursion depth exceeded in comparison. Maybe I should search this. See how much time I have. So offer you the context of the call, the cause error, design serves for debugging. Actually, this is not documentation of this behavior. Again, is something with recursion. My issue. I think the logic makes sense. Maybe I should put in the path as well here. That's the problem. Or RC not in path. Because I'm adding them here. Maybe that's the issue. And then I should. Okay, so it stops. Nice. Then I'm still getting the wrong one. So I guess this part is correct because first I check if it is in path. If it's not, I add. So it must be this thing that I'm getting wrong here. So in my mind, I'm checking if the current element. Yeah, but I'm checking the wrong way. That's the thing. Or maybe not because this stays fixed through the recursive calls, but I'm checking all the. Oh, that's the problem. I'm checking all the other coordinates. Oh, but it should be only on the horizontal and vertical that I'm increasing, decreasing here. So I don't think that's the mistake. So what's the issue here? Current. Or maybe it's greater? Or, yeah, but it has to be greater than the other heights to overflow into any of the oceans, I think. Or maybe it has to be adjacent to each one. Oh, but one is not selected here. Oh, because it doesn't go into the other one. Yeah, I think the main condition is has to be bigger than the adjacent cells in the vertical and the horizontal lines. So I don't see how this condition here is incorrect. And I'm getting the current element on each call, and I'm comparing with the traversal of the other elements in the right and left, in the right and the vertical and the horizontal direction. And then if any of them returns false, it should return false. Let me see if I return true here is gonna give me anything in the output. To see if it's not something else that I'm missing. So I'm still getting an empty, even if I return true here. So it's something else that I'm missing here. I guess I should put and on each one. Maybe that will change. True. No. So maybe it's because of this thing here. I just print this. It's returning none. Huh. So let me go back. Yeah, or whatever. I'm gonna look at the solution, then spend more than the time that I devoted for this.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve Pacific Atlantic water flow.
So this is another problem from the blind 75 list, and that's why I'm doing it today. The link to the spreadsheet will be in the description again, and so we will be able to fill in one more graph problem today from that blind 75 list. We're nearly done with that list now. At least most of the important problems on this list. I think there are some binary questions that I haven't really done, and I might not do these because I feel like binary questions rarely come up in interviews. But for this problem, so the text is a little small, so let's focus more on the picture. So we're given a two-dimensional grid of values, and so each value represents a height. So this has a height of 4, this has a height of 5, etc., etc. We are claiming that the top border of our grid, everything right above our grid, and everything to the left of the grid is going to be called the Pacific Ocean, and everything to the right of the grid and everything below the grid is going to be the Atlantic Ocean. So for any particular cell, we want to know, can this cell reach the Pacific Ocean and can it reach the Atlantic Ocean? If it can, then we are going to include this position in the result. If it cannot reach the Atlantic and Pacific Ocean, then we don't include it in the result. So how do we know if this cell can reach the Pacific and Atlantic Ocean? Because clearly there's a path, straight to it. Well, there's one condition. We want to know if water from this cell can flow to the Pacific and to the Atlantic, and water can only flow from the perspective of a cell to an adjacent cell that has a value that is lower than the original cell or equal to the cell. And it can only flow in 4 directions straight above, to the left, to the right, and below. That's pretty straightforward. Usually you can't go diagonally in these types of graph problems. And so in this case, for this 5, we see that the above neighbor 3 is less than 5, this is less than 5, this is less than 5, and this is less than 5. So clearly 5 can go to all of its neighbors. Now let's take a look at the 3. Okay, 3 has a neighbor 1. 1 is less than 3, so it can definitely flow in that direction. And now see, this 1 is bordering the Atlantic Ocean. So clearly that means 5 is able to reach the Atlantic Ocean. Now let's look left. It can reach 4, and 4 can definitely reach 2 because 2 is less than or equal to 4. So from this perspective, we can also now reach the Pacific Ocean. So water from this position can flow to the Pacific and it can flow to the Atlantic. So this position is going to be included in our result. So a brute force and naive way to solve this problem is to simply go to every single position, do some kind of graph traversal, DFS or BFS would probably work, and doing that search check from a cell, can we reach the top and left border, and can we reach the right and bottom border? And if we can, then we're going to add this cell to the solution set. If we can't, then we don't add it, right? So if we're doing a DFS or BFS on every single position, starting at every single position in the grid, we're going to get a time complexity of basically the size of the grid. Let's say that's n times m, which is the dimensions of the grid. And if we do that from every single starting point, we're going to get n by m squared as the big O time complexity. And you might think, well, since we're doing this recursively, we're probably doing a lot of repeated work, right? So for example, if I'm starting at 3, right, doing a DFS from here, I'm going to go to its neighbors and then do DFS from here, 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 and here. And maybe, by doing that, I can cut out the repeated work, right? And so we won't have to, restart a DFS for every single position in the entire grid. And you might think that that will work, but I'm pretty sure it doesn't. I'm not going to go through the details of why, and somebody in the comments can correct me if I'm wrong. Maybe there is a clever way to get that to work, but I tried to do it myself and I was not able to, so I don't know if it's actually possible to do it that way. There's a different clever way to solve this problem. How about, rather than us going through every single cell and checking if this cell can reach Pacific and reach Atlantic, how about we go start from the Pacific Ocean, right? And let's find every cell that borders the Pacific Ocean. Clearly, everything in the first row borders the Pacific Ocean, right? That means everything in this cell can reach the Pacific Ocean, and everything in the left column can also reach the Pacific Ocean. And starting from each of these nodes, what we're going to do is now find what are all the other nodes that can also reach the Pacific Ocean, right? So at the end, we would have, some kind of set, maybe, it looks something like this, right? Or whatever. And then we know, okay, these are all the ones in purple can reach the Pacific Ocean. And similarly, we would also do that with the Atlantic Ocean. We know everything here on the right side can reach the Atlantic Ocean. Everything at the bottom can reach the Atlantic Ocean. And similarly, we do some kind of graph traversal starting from each of these positions, right? And see, okay, what nodes can reach the Pacific Ocean as well. And at the end, we would want to go through every single position in the grid, and we'd want to find positions like this one that can reach the Atlantic and Pacific Ocean, that we marked as being able to reach the Atlantic and Pacific. And then from these ones that can reach both, we would add them to our result and then return the result. So that's kind of the general algorithm of how we're going to do things. The reason this is more efficient, this is going to be big O n times m. We're not going to be revisiting nodes several times. We're not going to be rerunning a graph traversal. What we're going to be doing is starting at each of these nodes, right? Doing a depth first search, right? So for example, let's say we started at this one, right? We do a depth first search and then see all the other nodes that can reach the Pacific Ocean, right? Let's say we marked these and these, right? And then maybe we do the same thing starting at this one, right? And we'd go over here maybe, and then go over here, and then we'd come back here. If we ever got to a cell that we revisited, we would not want to continue our depth first search from a repeated cell, right? So we just wouldn't do that. So that's the main idea of this algorithm. But there's one last point I want to make before I start going through the code, and that is, remember how if we're starting at a cell like this one, water can flow from this cell to a cell that has a smaller value, right? Like a small cell like 3, for example, and then it can flow down to a smaller cell like 1, and then it can reach the ocean, right? So if we are starting from a cell and reaching the ocean, we are allowed to go at equal heights, so 1 can reach 1, or we can go in decreasing heights like these ones. But if we're going in the opposite direction, if we're starting at the Atlantic Ocean and going to a cell like 1, going to a cell like 3, and going to a cell like 5, then we're going to have to do the opposite. We can go to cells of equal heights or cells of increasing heights, right? You kind of see why that's the case, because what we're saying is water is allowed to flow from 5 to 3 to 1, so therefore water from the ocean is allowed to go from 1 to 3 to 5. Because that does mean that 5 can reach the ocean. So with that being said, the first thing I'm going to do is go through the first row, which is going to be Pacific Ocean values, and then from there I'm going to run depth first search to see all the other nodes that can reach the Pacific Ocean. And I'm going to do the same thing at the bottom row, seeing which nodes can reach the Atlantic Ocean. And I'm going to be maintaining those in a set. Let's call it a visit set. It's going to be a hash set so that we don't end up adding duplicates to it. So now getting into the code. So the first thing I like to do with these problems is just get the dimensions of the grid. So we're guaranteed that this grid is not going to be empty, so we don't have to worry about that. So let's get the length of heights, which is going to give us the number of rows, and then get the number of columns as well. And so I'm going to be having 2 hash sets, Pacific and Atlantic, maintaining all the positions that can reach the Pacific and Atlantic Oceans respectively. And then what I'm going to do is I'm going to go through every single position in the first row. So I'm going to go through every single column in the first row, right? And what's going to be every single position in the first row? From here, it's going to be zero, right? In the first row is 0, and column is going to be the column position. And so what I want to do on this position is run a DFS, right? So I'm going to run a DFS on this position, right? And so I'm going to pass in a visit set to this DFS function. Since this is the first row means it's the Pacific Ocean, right? It's not the Atlantic, it's the Pacific. So that's what I'm going to pass in as the visit set, the Pacific Ocean. So I want to visit this position, and I want to see all the other positions it can reach. Now, we know that water from the ocean to other cells can only go at equal values or greater values, right? Remember, we reversed the thinking. Since we're going from the ocean to the cells, we're going to have to do the opposite. So we can go to greater cells. So I want to always pass in a previous height variable to this. So if we're going to visit a cell, I want to make sure that we're allowed to visit that cell. So I'm going to pass in a previous height. So since there is no previous height for this position, I can just give it a default value, and I'll just give it the same height as this position because that's going to be allowed. Remember, we're always allowed to visit heights of the exact same height as the previous position. And so while we're at this, right, we're going through every position in the first row. Why not go through every single position in the last row, which tells us the Atlantic Ocean, right? So what's the last row? It's going to be the number of rows minus 1, and going through every column in that row. And so instead of passing in Pacific, let's pass in Atlantic, because the bottom row refers to the Atlantic Ocean. And similarly, we'll pass in the height of this position as the previous height. So we're calling this DFS function, so let's might as well define it up above here now. The first 2 parameters are going to be the row and column, and the next is going to be the visit set. Now, since we're reusing this function for both Atlantic and Pacific, we'll just give it a generic name like visit. We could be passing in either of these 2 sets. And the last parameter is the previous height. So if this position has already been visited, meaning if row column is in visit, then we're going to return. We're not going to continue this function. Or if it's out of bounds, we're also not going to return, right? Because remember, we're already going from the ocean, from let's say the Pacific Ocean, and trying to visit all the cells that we can, because that's going to tell us all the cells that can reach the Pacific Ocean. So we're not even trying to reach the ocean right now. We're going from the ocean to all the cells. So if we go out of bounds, then we're going to have to return. So if let's say R is less than 0, or C is less than 0, or if R is equal to the number of rows, that means we've gone too large. Or if C is equal to the number of columns, that also means we've gone too large. And the last case where we would want to return is if the height of this position, row column, is less than the previous height. Because remember, we're only allowed to go to heights of greater height or equal. So if the height was too small, then we would want to return. If we're not returning, that means we're finding a new cell. So let's go ahead and add it to visit. We're visiting this new cell, row column. And then on all 4 of its neighbors, we also want to run DFS on all 4 of those neighbors. And we can do that with a loop, but I'm lazy, so I don't want to write that out. I'm just going to copy and paste this 4 times. So row column, passing in visit, and passing in the previous height, which is just going to be height at this position, row column. Let's copy and paste this 4 times. And so we're going to go through all 4 of its neighbors. So row plus 1 is one neighbor, row minus 1 is a neighbor, column plus 1 is another neighbor, and column minus 1 is another neighbor. And that's going to be the entire DFS function for us. It's going to be marking all nodes that can reach the Pacific Ocean or the Atlantic Ocean, depending on what we pass in. And so right now we're doing that for the first row and the last row, but we also know the first column is going to be the Pacific Ocean, and the last column is going to be the Atlantic Ocean. So let's do that. So for every row in range of rows, we want to get every position at the leftmost column and call DFS on it. So for row, we're just going to pass in the current row. We're going to go through every single row. And for column, we're going to pass in 0, right? We know that the first column is 0, and the first column can reach the Pacific Ocean. So that's what we're going to pass in, and for heights, just going to give it the default value of this position. And similarly, let's do the same thing for the last row. Let's do the same thing for the last column. So for columns, instead of 0, let's do columns -1. And instead of Pacific, let's pass in the Atlantic Ocean because that's what the rightmost column refers to. And heights is going to be the same default value. And so we don't have to rewrite the DFS function, right? Because we already wrote it up above here. We're reusing that function. So once these 2 loops have executed, we will have marked every single position that can reach the Pacific Ocean in here, and we'll have done the same with the Atlantic Ocean. So now after that, let's just go through every single position in the grid, brute forcing it. So every single position, every single row, every single column. And for every single position, we want to know if this position, row, column, is in the Pacific Ocean, and if row column is in the Atlantic Ocean. Then what we want to do is let's first declare a result list. If this position was in both Atlantic and Pacific, we want to go ahead and add it to our result, and we want to add it as a, let's say, a sublist. And so once we've done that, then we have definitely found out every single position that can reach both Atlantic and Pacific Ocean, and then we can go ahead and return that result. Okay, I had a pretty stupid bug, so sorry about that. So when we're passing in, we're finding the position of height. So we have column because that's what we're at. For row, we should have 0 because that's the position that we're starting at. So sorry about that. Let's change this to a 0. And similarly down here, I actually think we have this right. So rows -1 because that matches over here. But down here we have row and column 0. So we want to change column to a 0 over here. And over here we do have row, so that matches. But columns -1 is the column value that we want to pass in. So with those changes, you can see that this solution does work, and it is about as efficient as you can get for this problem. So I hope that this was helpful. If it was, please like and subscribe.
I didn't fully understand this part here, but I guess it's the same thing, same logic I was trying to apply there, but with the exception of the first row, these 2 for loops here, for the boundaries. And then at the end, but for some reason I still don't understand why mine, because I did something similar here, but I separated in different if statements. It's pretty much the same thing. I mean, I think I did probably on the reverse order, but even then, and here he's just returning as well. Yeah, so I'm not really sure the difference. If RC back and RC it. Also, if it visits, that's the difference. He added to the path, to the set after the return statement. So it only adds the visited paths if it passes the check on all of them. Yeah, I still don't understand, but I have to go to the other one. Course scheduled, let's see, 44. I'm starting to think it's gonna be very difficult to learn Vim while I do this stuff, because it might take a lot longer than I was expecting. But maybe I should, next time I go, after I study a bunch, then I should just try to get familiar with at least the basic key shortcuts for Vim while I was trying to solve these problems. There are a total of num courses you have to take, labeled from 0 to num courses -1. You are given an array of prerequisites where prerequisites I equals this, indicates that you must take course B, I first if you want to take course A, I. For example, the prior 0, 1 indicates that you take course 0, you have to take course 1. Return true if you can finish all courses, otherwise return false. So these are the courses you have to take, and these are the prerequisites, which are a list of lists. Prerequisites, so there are a total of 2 courses you should take. Damn, this sounds really hard. So pretty much the prerequisites determine the path on this one. Yeah, but it's still not really clear instructions. Is it only zeros and ones? Let me just run the thing to see the task case. 1 0. I assume it's gonna be the same pattern as the other ones, probably. So maybe rows calls again. If prerequisites, prerequisites 0. We're gonna have DFS, row columns. I forgot about this here. Then you're probably gonna have some if statements here. If 0 or 0 or I equals rows or C equals calls. Turn. Then here you're gonna call in all directions again. It's not that difficult if you think about it. Once you once you capture the fundamental patterns that the problems, these types of problems use, it becomes pretty much the same thing, I think, in all of them. Just do the same stuff, and the only thing that changes is the if-else conditions to check for the flow of execution, depending on what logic you're trying to put into the graph. So it's not that hard, actually, if you think about it. The hardest part is becoming familiar with the main principle, I think. And to wrap your head around that. So here, and I should have probably a set then. Visitor, set. So let me think now. The tricky thing on this one is the path here. To understand the logic of the path, of the prerequisites, because it's a little bit confusing. But I think this part is pretty much the same, and then depending on the logic here, you're gonna put something here to add the path, just like in the other one. Your total of 2 courses you take. To take course 1, you should have finished course 0. So it is possible. Your total of 2 courses you take course 1, you should have finished course 0. And to take course 0, you should also have finished course 1. Yeah, this is confusing. Because this is basically a loop, but... So maybe if the beginning is equal to the end of the path, then it is invalid. I think, yeah. So if the beginning is equal to end is invalid, and if the num courses is lower than the length of the path. So if the path is bigger than the courses, it also is also invalid. So how can I structure the visited? Each path is gonna be a list probably. So it always goes from the first one to the second one. And then from the second to the... So it's always in zigzag. So maybe I don't need to do these 4 calls here. I can just move in zigzag. I don't like this explanation here. I think they should have used different examples, because it's a little bit unclear from these examples if what kind of inputs are gonna be, how many paths exist, how many prerequisites are gonna have. Maybe the constraints here. It's always gonna be true. Oh, so the list is always gonna be true. And it's less than 5,000, so it means that you can have a lot of them. So I think it's a different logic, actually, than this thing here. Because the end of one path is equal to the beginning of the other one. Or maybe not. Also, all of them are unique. Yeah, so actually in the columns, I'm not gonna go up. I'm just gonna go down because I'm gonna start at the top, I think. Let me think. I also probably need to pass the number of courses into this call here. Yeah, so I can pass I here, or I less than 0, and then I decrease the I each time. And here I would pass 0, 0, I. So if I start at the top, 0, then I go 1 to the right, and then down. Then 1 to the right, down. But I can't start in the 0 position again. Maybe I can, actually. What if I always start at 0 here? And I just traverse through. I start at 0 first. 0, and then I go 1 to the right. And then 1 down. And here I remove this stuff because it's unnecessary now. So the way that I'm thinking is I'm trying to think about a way to go into zigzag and put the conditions that I wrote here. How I'm going to start this on the sat. So maybe it has to be after this calls here. But then The other thing is I just realized that I can put the I here because if I decrease the I in each call, then it doesn't work for this thing here. Let me think. I think the two main conditions is the path, the number of courses that should be equal or greater to the path, and it can't be cyclical. So the end of the path can't be the same as the beginning. But the question is, how can I capture that? Because it needs to be after, I think, here, then. And maybe this doesn't make sense as well. I just realized that because I'm calling recursive with 0. It's not increasing or decreasing each one. So maybe that's the thing that I'm missing here. Because I think the rows have to come. The amount of times that is going to traverse here has to come from the outside. The number of courses, which is going to be divided by 2. Maybe I don't need to divide it. I can just pass row plus 1. So let's say if I start on here. I start on the beginning one. Then I go plus 1. But here also has to change. That's the thing. So maybe both of them are I. So it starts at 0, 0, but then I'm moving diagonally. I can't do that. And the only thing that I can change, I think, is the columns in each iteration. And I should probably be changing that outside. Yeah, I think I'm confusing both the recursive call and the loop here. But the logic, I think I understand. You traverse through the prerequisites and then you check if the path, check these two conditions. If either one of them fails, you return false or return. If not, you just add the path to the visited set, I think. So I think I'm gonna look at the solution. Yeah. I'm gonna go to the bathroom first. Schedule.
Hey everyone, welcome back. Let's write some more neat code today. So today let's look at a graph.
I think I'm gonna try to finish.
Hey everyone, welcome.
Oops. I'm gonna try to finish the graph ones before I stop this time, and then gonna go read the book. I'll be right back. I think if I can get through anything greater than 55 today, I'm happy. It's gonna be difficult, but because then maybe I can finish this list by tomorrow. And I might spend a lot of more time reading after I finish the thing. Like focusing on one thing and then making sure that I read the whole chapter about that thing, the data structure, as I study about it.
Graph problem, actually. It's called course schedule. We're given a total number of courses, and these are our nodes, and they're labeled from 0 to n-1, basically. So some courses have prerequisites. For example, if you want to take course 0, you have to first take course 1, and that's represented as a pair or as an edge in our graph. So if you want to take course 0, you have to first take course 1. And the only question we want to answer is it possible for us to finish every course? So let's just look at the first example. We're given number of courses are 2, so that means we have one course 0 and another course 1. We know that the prerequisites are like this, meaning that if we want to take course 1, we have to first take course 0, and I'm going to represent it as an edge going outward from 1 into 0. So what do they mean by possible? Let's just run through each of our courses and see, is it possible to take each one? So for 0, is it possible to take 0? Well, we don't have any outward edges from 0, so that means 0 does not have any prerequisites. So it is possible for us to complete course 0. Then we look at course 1. It has one prerequisite, which is 0, and we know 0 is possible to complete. So once we finish course 0,
This one is the Chinese version, I think, of LeetCode. Has some of the free problems for the premium problems for free. But I don't think I'm gonna do it because I have to sign up, and I don't have an account. So I think I'm gonna skip this through other ones, which gives me more time actually. Okay, so this also doesn't work. Dynamic programming. All right. Okay.
then we're allowed to take course 1, which has no other prerequisites, right? The only prerequisite was course 0. So therefore, both of these courses are possible to complete, so we can return true. So let's look at an example where it's actually impossible. So we're given n equals 2. That means we have 2 courses, 0 and 1, and we're given 2 prerequisites, so 1, 0 and 0, 1. This one means that if we want to finish course 1, we have to first complete course 0. So 0 is a prerequisite. The second one means that if we want to finish course 0, we have to finish course 1 first. So 1 is a prerequisite of 0. So the problem with this is kind of obvious, right? There's a cycle. So if we want to finish course 0, we got to go finish course 1. If we want to finish course 1, we got to finish course 0, and it just goes like that forever. So neither of the courses are possible to finish. So in this case, we return false. So we can actually solve this problem using depth first search. We can also use breadth first search, and I'm going to show you just the depth first search version because I like it better. So given this new example, the first thing you want to do is visualize it. So I'm going to draw a picture. So we're given 5 nodes. So we have 0, 1, 2, 3, 4. That's 5 nodes. We're also given 5 prerequisites. So in this case, we end up having 5 edges, right? From 0 to 1, 0 to 2, 1 to 3, 1 to 4, and 3 to 4. So my goal here is for each of these nodes, I just want to know, right, for each of these classes, can we complete this course or not? And how do we know if a course can be completed? Well, just looking at this picture, it's obvious, right? 0 has a prerequisite of 2, but 2 does not have any prerequisites, which is great. It also has a prerequisite of 1, and 1 has 2 prerequisites, 3 and 4. 3 has 1 prerequisite of 4, and 4, luckily for us, does not have any prerequisites. So looking at this, it's kind of obvious that we can complete all these courses. So let's do the algorithm to be able to determine that. We see that these are kind of our base cases, right? 2 and 4 don't have any prerequisites. That's useful information, but we don't need a graph to tell us that. We can use a data structure called an adjacency list, and I'm going to call it prerequisite map because the data structure I'm going to use is a hash map to represent this. So for each of our courses, we are going to have a list of all of its prerequisites. So for 0, we know 0 has 2 prerequisites, 1 and 2, and we're going to repeat that for every single course. So for 1, we know that 2 does not have any prerequisites, so we can just put an empty list over here. 4 also does not have any prerequisites, so we get another empty list. So now we're going to run depth first search on every single node. I'm going to do it in the order from 0 to n minus 1. So we'll be starting at 0, so we're going to run depth first search on it, right? How are we going to do the depth first search? Well, we have our prerequisite map, so we're going to do it recursively. We see that it has 2 prerequisites, 1 and 2. So now let's run depth first search on the first neighbor 1. So now we look at 1, we see that it has 2 neighbors, 3 and 4. So let's recursively run depth first search on its first neighbor 3. So since 3 is a prerequisite of 1, now we want to know if we can complete course 3. So we look at its prerequisites. It only has 1, 4. So now we're going to check its only prerequisite 4. Can we complete course 4? And then we want to look at the prerequisites of course 4, which we know are empty. This is good, right? So now we see that this is empty. So what does that tell us? That tells us course 4 can be completed, which we basically already knew because course 4 has an empty prerequisite list. So I'm just going to put a little check mark here to say that we know course 4 can be completed. And so recursively, we're going to end up going back to our 3, and we see that it only had 1 prerequisite, and we were able to complete that prerequisite 4. So therefore, 3 is also a course that can be completed. And so what we can actually do is from its prerequisite list, we see 4, we can just remove the 4. We know it can be completed. And so I'm representing that by having an empty list here, right? Just an empty list means that it has no prerequisites, therefore it can be completed. So I removed the only prerequisite that 3 had. Then from 3, we can actually go backwards to 1, which we see here. We can kind of get rid of this 3 because we know 3 can be completed. And then from the 3, we're going to end up going to 4 to check again if 4 can be completed because it is a prerequisite of 1. And since we already know 4 can be completed, we can get rid of that as well. So now we know for sure that 1 can also be completed. And now I'm going to go back to 0, which is how we even got to 1 in the first place. And we look at the prerequisites of 0. We see 1 is no longer a prerequisite because we basically know that 1 can be completed, but we still have to look at this 2. So then we're going to go to the last unvisited node in our entire graph, which is 2. So now we've gotten to the last course 2. We see it's an empty list, right? Therefore, 2 can be completed. It has no neighbors. It has no prerequisites. So I can put a little check mark here. 2 can be completed. And then we can finally go back to our original node, 0, cross out its last prerequisite, which was 2. And now when we look at 0, even 0 has an empty list of prerequisites. Therefore, we know 0 can be completed. So since we were able to complete every single course, that means we can return true. Every course is completable. And the time complexity for this is going to be big O, the number of nodes we have, which is n. I'll use n as that. And I'll use p for the number of prerequisites that we had. Because if you notice in this graph, we have to visit every single node, and we have to move along every single edge. And once we get rid of the prerequisites from here, we don't really have to visit a course twice because once we know it can be completed, we can instantly do that. We don't have to go through its prerequisites twice. So I'm going to show you one last example. This is the example that what we're going to do. How are we actually going to detect this loop? Because we see, so I'm just going to cross this stuff out because we're looking at a different example. But here we see that 0 has a prerequisite of 1, 1 has a prerequisite of 2, 2 has a prerequisite of 3. So this is a loop. We cannot complete these courses, but how can we actually detect this loop? I'm going to show you how really quickly. So to detect a loop, I'm going to use one last data structure, and it's going to be a set. Though I think you could just use an array if you want. I'm going to call it the visit set. And all it's going to contain is the list of courses that we're currently visiting along our depth first search. So let's say we start at 0, then we add 0 to our visit set. We take a look at the prerequisites of 0. We see it has 1 prerequisite. So then we move to 1. So now we visit 1. So we're going to add 1 to our visit set. And we look at the prerequisites of 1. It has 1 prerequisite 2. So then we move to 2. We run depth first search on 2. So to do that, we have to first visit 2. So 2 is also going to be added to our visit set. And lastly, we see 2 has 1 prerequisite of 0. So then we, of course, want to visit 0. And so now we're going to visit 0 twice. But you see that 0 is already in the visit set. Therefore, we detected a loop. Therefore, we have to return false. These courses cannot be completed. So now let's finally look at the code. So the first thing I want to do is create our pre-map. So our list of prerequisites. So we know for each course, initially we can set it to an empty list. So an empty list of prerequisites. And we want to do that for every course that we got, which the number of that is just number of courses. So this is, if you're not familiar, this is some Python stuff. I'm just saying that for every course, initially we want to map it to an empty list. And we know that the prerequisites are actually contained in this nested list variable. So let's iterate through that. Let's get each course prerequisite pair from that list and then just start appending them. So pre-map, of course, we want to append to this list this prerequisite. So we also want a visit set, which is going to store all the courses along the current depth first search path. And of course, it's initially just going to be empty. So since we're going to do this recursively, I'm going to define a nested function, depth first search, inside of our can-finish function, because then we'll have access to all these variables without having to pass them in as a parameter. The only parameter that we have to pass in is the current course that we're visiting. And so like most recursive functions, we want to look at our base cases first. The first base case is if course is in the visit set already. So what this means is that we're visiting a course twice. So we detected a loop, so we can return false, meaning that this course cannot be completed. The other base case we know is if the prerequisites of this course happen to be an empty list. What that tells us is that this course has no prerequisites, and we can return true because it can definitely be completed. If neither of these conditions is satisfied, then we can take this course
and add it to our visit set, because that means we are currently visiting this and we're going to recursively run depth first search on its prerequisites. So I'm going to loop through the prerequisites of this course. For each one, I'm going to run depth first search on it. So depth first search on this prerequisite. If it happens to return false though, then we know we can return false immediately. We don't have to wait, because if we find one course that can't be completed, then we can return false for the entire function. So I forgot to put a not over here. So if not, meaning if it returns false, then we return false. But if this does not execute, that means it's a course that can be taken and we want to return true in that case. But before we return true, we want to remove it from our visit set because we are no longer visiting this. We've already finished visiting it. So visit, remove this course. And also, since we know this course can be visited, what we can do is say pre-map, we can set it to an empty list so that if we ever have to run depth first search on it again, we will, in that case, execute this condition and return true immediately. We will not have to repeat all this work of running depth first search on its neighbors. So that's all for our depth first search function. The function is done. All we have to do is call it now, but we have to potentially call it for every single course in the number of courses that we have. And if any of them happen to return false, then we have to return false immediately. And if they don't return false, then we can return true. All courses can be completed. And the reason we are looping like this is mainly because what if our graph is not fully connected? Like what if we have a graph like this, 1 has a prerequisite of 2, and maybe 3 has a prerequisite of 4. So these are 2 separate graphs that are not connected, right? So we have to manually iterate through every course and check, can 1 be completed, can 2 be completed, can 3, and can 4 be completed? So this is the depth first search solution. You can see that it does run very efficiently, about as efficiently as the breadth first search solution as well. And I hope this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.
I can tell I'm already getting tired. So I think I'm gonna do one more and then pause and then continue after that. Yeah, I wanna see if I can get to 55 today. Or maybe even more, so I can finish tomorrow the list. And then start diving deeper into each one. You are climbing a staircase, it takes n steps to reach the top. Each time you can either climb 1 or 2 steps. How many distinct ways can you climb to the top? I think I've seen this problem before on the Zero to Mastery course, but I don't remember really well. I know it's going to involve a recursion call. It's going to involve recursion, but I'm not sure how to do it. Takes 10 steps to reach the top. Each time you can either climb 1 or 2 steps. And how many distinct ways can you climb to the top? There are 2 ways to climb to the top. 1 and 2 steps. To climb to the top, 1 plus 1 plus 1 plus 1. So permutations are allowed. What's the domain? Dynamic programming. So I think it's pretty similar to that backtracking stuff from before, where it's separated into lists. I already forgot the logic behind it. So pretty much I have to divide by the thing that is that the order matters. So I need to get the remainder of the division, or the quotient of the division, plus the stop, and then any combination of that. Yeah, but that's probably not a good way to approach this. So what's another way? I think I'm gonna have to create a different function and then a set probably, or at least to append the paths possible. Yeah, I remember he adds something. Yeah, it was to find. Oh, I forgot. Oh yeah, it's to find the sum to the target. All the possible sums to the target. And then he added the frequency into a list, I think, based on how many times it was used. Yeah, that's how, and he created a tree based on that. So maybe, and it's gonna have if routes if stop what's in routes stop and then I should probably make n if maybe I create a different variable and start outside total 0. Yeah, I think I remember now. I'm remembering. And then I'm gonna make total plus equals 1 at the end. Or plus equals stop. And then I make if total minus stop or equal to 0. Total minus n. Or n minus total, actually. Return. And then here I call recursively with... But then how do I choose this stop? That's the thing. I stop plus 1. Path stop plus 2. And then I can erase this. So each time I run this, I increase the total based on stop. Then I check to see if, yeah, but this is probably not a good idea because I'm only, I should add regardless, I think. I think the only thing that I'm missing is I need a way to keep track of the stops. I need a hash map, I think. So maybe I should create a stat. Yeah, and then here I return. So visited equals sat. So if it's equal to 0, I append visited.add routes. If routes being visited. Return. I'm not sure if this is gonna work, but because I need to check if the amount of things, the frequency of the steps was visited already or not. And also here, this recursive call, I'm not really sure how to check for all combinations possible. Maybe this works actually. And then I just need to figure out how to call at the end or return in the main function for n. The step is gonna be 1. Oh, it can be +2 then. So it has to be either this. Yeah, but then how do I increase the step? Or make it like this? I feel like this step here is probably incorrect. And maybe I should be creating another variable instead of here, instead of the total. But then I don't capture all the combinations. That's the problem. I could just call path1 here and return visited, but it's obviously not gonna be the solution. It's not gonna work. Yeah. It's probably something like this. I think I'm just gonna check, even though I still have time, but
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve climbing stairs. So this is going to be another dynamic programming problem, and this is definitely more on the easy side, definitely compared to some of the really hard dynamic programming problems that we've been solving recently. But I still think that this is a good problem to really understand the fundamentals, understand, the brute force, and taking that brute force, using memoization, and then of course getting the true dynamic programming solution. And by the way, if you don't already know, we have been tracking a list of blind 75 questions on this spreadsheet. So today we're going to be solving this dynamic programming one, the climbing stairs problem. So I will be adding the solution once this video is uploaded. And the link will be in the description if you do want to take a look at this sheet. So the problem statement is pretty simple. We're climbing a staircase, and it's going to take us n steps to reach the top of the staircase. Every time we take a step, we have two choices of how we can take a step. We
can either just take one single step or we can take 2 steps at once. And all we want to know is how many different ways can we get to the top of the staircase. So let's look at the first example, n equals 2. That means we need to climb 2 steps. So we could draw the picture kind of like this, right? So let's say we start over here, right? This is step 0, basically, when we haven't climbed anything. And our goal is to get up here, which clearly is 2 steps, right? So starting from here, we know we can make 2 choices, right? We can take 1 step and that would land us over here, or we could take 2 steps and that would land us over here. So already we're seeing one way is to just take 2 steps, right? That's what this path would take us, right? That's one way we could reach the goal, right? Just taking 2 steps at once. Now, if we ended up taking 1 step, then we would be at this position. So from here, we would have that same exact choice, right? We can take 1 step or we can take 2 steps. Now, clearly, if we take 2 steps, we've gone too far, right? We were only trying to climb 2 steps total, but if we end up over here, then that's not going to count as a path, right? So that would not count. But as you can see, if we took 1 step initially, then we could take another single step, and that would be another way. So either this is one way we could reach 2 steps, or we could just take a single double step, right? So clearly, there are 2 different ways we could climb the staircase, and that's also the result of this problem, and they basically explain it over here. So let's look at the second example, which is basically if we were climbing 3 steps instead of 2, right? So let's look at the drawing. So once again, we're going to do the exact same thing that we did, right? From here, we could take 1 step, or we could take 2 steps, right? And so far, we'd get here. But remember, our goal is to climb 3 steps, so let's continue. So from here, we could take 1 step, which would land us at the result, or we could take 2 steps, which would get us out of bounds, right? That's not what we want to do. So far, we have found one way to get us to the result. But let's continue that from over here. Again, we can take a single step, which would get us over here, or we can take 2 steps, which would get us at the result. So now we found 2 different ways we can get to the last step. And lastly, we still have a path to continue, right? We got here by taking 1 step and then taking another single step. So here we have 2 choices: take 1 step, get to the result, or take 2 steps and get out of bounds. So in the end, we see that there were 3 different ways we were able to get to this last step. As you can see, this is getting really hard to visualize with a single staircase. A more easy way would be to get a decision tree to visualize. And at every decision, remember, we can take 1 step or we can take 2 steps. So let's try to visualize the problem like that and see if we can notice any patterns. So let's say we're given n equals 5. We're trying to climb 5 steps. So we can consider, just like the previous drawing, that we're starting at step 0 and our goal is to get to step 5. Now remember, at every given point, we have 2 decisions to make. We can climb 1 step or we can climb 2 steps, right? And depending on the decision that we make, each of these is going to lead to a different path we can take to get to the result. And remember, all we're trying to do is count the number of ways we can get to that result. So in this decision tree, we're going to keep making 2 decisions at every step, and at the end, we're going to count how many different ways were we able to get to 5 steps reached. So we can get to step 1 and we can get to step 2. Let's just continue drawing out the decision tree. From here, we can make 2 more decisions. We can take 1 step, which would get us to 2. We can take 2 steps, get us to 3. And similar here, we can take 1 step, get us to 3. 2 steps, get us to 4. From here, we can also take 1 step, get us to 3. 2 steps, get us to 4. 1 step, get us to 4. 2 steps, get us to 5. Now here, we can see that we reached the result, right? N equals 5. So this is our first path that we could reach to get us to the result, right? You can see we took 1 step, then we took 2 steps, then we took another 2 steps. So this is our result. Once we get to it, that's our base case, right? We're going to solve this recursively, right? That's pretty much what we're doing. This decision tree is basically recursion, and this is our base case. We wouldn't want to continue if we got here. So here we would return 1. We found one way to get to the result. But for the remaining paths, let's continue. So here we can take 1 step or 2. That gets us to 4. This would get us to 5. So you can see once again, we found another way we can get to the result. So far we have 2 different paths that can lead us to step 5. And here,
All of these problems are pretty much the same thing and are variations of the same thing. And they all seem to be, the fundamental things seem to be recursion and trees, this dynamic here of these branches. So that's probably the most important for and the highest ROI to solve all these different problems. Should focus on these recursion techniques.
let's do the same thing. If we take 1 step, we get to 5. That's the result. If we take 2 steps, we get to 6. That means we overshot, right? We went too far. This is another base case. If this number of steps ever exceeds 5, then we're going to return 0, right? We found 0 ways from this path that can reach the result. So now let's continue. Over here, again, we take 1 step or 2, so we'll get to 4 or 5. Another path that leads us to the result. And here, we can also take 1 step or 2, which would get us 5 or 6. Similarly, over here, right? This is another 4, so the exact same thing is going to happen. You start to see we're repeating the exact same problem multiple times. How can we better solve this problem knowing that? So now we have another 4. We're just going to repeat the exact same thing that we just did before, right? Take 1 step or 2. We know we're going to get to a 5, and we know we're going to get to a 6. So you can see every path led to the base case except for this last one. So let's complete this. We can take 1 step, which would get 5, or 2 steps, 6. Okay, so now our entire decision tree is complete. So what's the result going to be? Remember, red means we're going to return 0. Green means we're going to and down to the power of n, that's not super efficient, but over here, we're asking how many different ways, starting from 2, can we get to 5, right? And down in this decision tree, we found, yes, there were 3 different ways, right? So then when we get over here, why do we have to recompute the exact same thing? Take a look at these 2 purple blocks I just drew. Notice how this decision tree looks the exact same as this one, because in both cases, we're solving the exact same subproblem. And since we're doing it depth first search, this one is going to be solved first, right? So if we solve this entire problem, what we said was, okay, we found out starting at step 2, there were 3 different ways to get to step 5. So when we get here, why don't we just take that result, store it in memory, store it in DP, or basically this is a cache, right? We're storing it in memory. So then when we get here, we can just say we already know the result of this, meaning that we don't need to draw out the entire decision tree. We're just going to skip that altogether. We're not going to draw this, we're not going to draw that, and we're not going to draw any levels of this tree. So as you can see, I'm eliminating all that repeated work by saving that solution. But that's not all, right? We see over here, we're asking a different subproblem starting at step 3. How many different ways can we get to n equals 5? Well, in this case, it was 2 different ways, right? Notice how this decision tree is the exact same over here, because here we're asking that same question starting at step 3. What's the number of ways? And since we're doing the step for search, this one is going to end up being computed before this one. So when we get here, we can just say we already know the answer is 2. So we don't need to run through the entire decision tree again.
So I think I get the logic here. So it's pretty much the same thing, but whenever you get to a unique step, you're gonna create a specific key value pair for that unique step, and then the remainder portion of the tree is gonna be the same as from if you went through a different route. So it's pretty much minimizing the size of the tree based on unique values of the decision tree.
So in this case as well, we can eliminate that repeated work. So I'm just going to cross this entire thing out. And we're not done yet. See over here, we're asking starting at step 4, how many ways can we get to 5? That same problem is over here. Notice how they have the exact same decision tree. This one is going to be computed first because we're doing depth first search. So once again, let's eliminate this repeated work. So now you can see when we do eliminate all that repeated work, this is what our decision tree ends up looking like. And this is roughly O of n. This is linear time solution. Reason being, we're only solving each subproblem once, right? So we know that the first subproblem, the original problem is starting at 0. Then we get a subproblem of 1, 2, 3, visualization. Can actually be solved with a true dynamic programming solution. As you can see, starting at the result, the result of 0 depends on the subproblem, this one, right? And this subproblem depends on another subproblem, which depends on another subproblem, which depends on another subproblem, which depends on our base case. So why don't we start at the bottom, solve the base case, and then work our way up to the original problem at 0, right?
It also makes me think that all combinations and permutations problems can be structured in this way and it's probably much better to think about it this way, of decision trees. So maybe the itertools library and the itertools and combinations from Python applies the same principles. So I think I'm going to look at, when it gets time to study more in depth, I'm going to look at those methods and see the correlation, try to draw the correlation from then and from this logic here of creating decision trees to solve these problems.
We start at the bottom, work our way up. This is called a bottom-up. This is called a bottom-up dynamic programming approach. So that's what I'm going to show you. We're going to start at the base case and then work our way up. So remember, we're starting at position 0, and our goal is to get to the 5th step, right? Each time we can take 1 step or we can take 2 steps, right? So I'm going to be storing our result in an array called dp. So we're going to have a position in dp all the way from index 0 all the way up to index n, which is going to be our input value, remember? So remember, we're at the base case initially, right? What's the base case going to be? Well, at the last step, if we start here, how many different ways can we land here? Well, that's just going to be 1, right? That's our default value. So now that we solve that, we are able to solve this one, right? Because remember, this problem depends on the subproblem of this. So from here, let's say we're starting here, we can take 1 step, which lands us at the result. We can take 2 steps, which lands us out of bounds, right? So how many different ways from here can we reach the goal? Again, it's going to be 1. And you notice how this is always going to be the case, even if we had something like n equals 100. So let's say this was actually 100 and this was 99. This would always be 1, right? This is always going to be 1 because it's at the goal. And starting from here, it's also always going to be 1 because we can take 1 step, which would get us to the result, or we can take 2 steps, which would get us out of bounds. So no matter what the input value n is, this is always going to be the case. It's always going to be 1, 1. Next, we're going to get to the interesting part. So then we want to know, okay, how many different ways from here can we reach 5? Well, this depends on 2 subproblems which come after it, right? So we can take 1 step over here or 2 steps over here, right? So, and then we get to the subproblem, right? So from 4, we don't need to continue to figure out how many different ways from 4 can we get to 5 because we just computed that. That's why we're using dynamic programming. That's why we have this array, because we already computed starting at 4, how many different ways can we reach 5? And we also, starting at 5, how many different ways can we reach 5? That's also 1. So what we're going to do in this value is basically take these next 2 values, add them together, 1 plus 1, and then we're going to get 2 over here. And we're going to do the exact same thing for this position too. So we know here we can take 1 step or 2 steps, right? So what we want to do from here, 3 is find out how many different ways can we reach 5. We just computed that, that's 2. And from 4, we want to know how many different ways can we reach 5. We also already computed that, that's 1. So what we can do is take these 2 values, add them together, and that's going to be what we put here. So starting at 2, we can get to 5 3 different ways. And at this point, I bet you probably get the idea. We're going to do the exact same thing over here. So what value are we going to put over here? Just take these next 2 values, add them together, 3
Isn't that the Fibonacci sequence?
plus 2 is going to be 5. And remember, this is what we were originally trying to compute. This is going to be
Damn, I think this is the Fibonacci. Huh. Interesting. It also makes me think that all the problems in the universe can be solved with recursion, because it's pretty much capturing fractal patterns between steps based on the possibilities and the complexity of the thing that you're trying to analyze.
be the result. It depends on only 2 subproblems which are listed right after it. 5 plus 3, that's going to be 8. So that's the result. If you're familiar with what the Fibonacci sequence is, the Fibonacci numbers, that's exactly what we're doing right now. We're starting at the base case of 1, 1, adding these 2 values to get the next result. Then we're adding these 2 values to get 3. Then we're adding these 2 values to get 5. Then we're adding these 2 values to get 8. So you may or may not be familiar with it, but that's what we're doing. And you may have also noticed we're using extra memory, right? We're having an entire array size equals n. That's going to be O of n extra memory. But is it actually needed to have an entire array? Notice how each value, such as this one, only depends on the 2 values that come after it. And this one only depends on the 2 values that came after it. So in reality, we don't need to have an entire array. We just need to have 2 different variables. Let's initialize the 2 variables like this. 1 is going to be this position. 2 is going to be this position, because starting from here, we want to know how many different ways could we reach the result. If we took 1 step, that's why this is called 1. And if we took 2 steps, that's why this is called 2. And we're basically going to be computing this next value, right? And once we compute this next value, we're going to shift our 1 variable over here, and we're going to shift our 2 variable over here, and we're going to keep doing that until we get to the result of 0. And if we initialize 2 initial variables, 1 and 2, as values 1, how many different values do we have to compute that come after it? In this case, you can see we have to compute 4 values, right? So basically, we compute n minus 1 values. We have to loop n minus 1 times, and then when our 1 variable ends up getting in this position, that's what we're going to return as the result. So this was a really long explanation because we did a lot of analysis, but when I actually show you the code, it's going to be really...
Damn, I think this stuff also made me think about a different thing about fractals, which is if you imagine as if each number being in the boundary, and then the steps between them are the logic of the function, the recursive function, the flow of if-else statements that usually happens in the recursive function as being the geographic mapping of the fractal. I think that's pretty much what's happening here. So, and it has a lot to do with the stuff that I want to do in the future. So that's probably the stuff that I'm going to spend most of the time thinking about. It's extremely interesting. because pretty much what changes is both the size of the step, let's say, in any recursive problem, the gap of the tree values from one node to the next, and the flow of execution, which is going to determine the geometry of the connection between those two nodes. And I think this probably can be used to solve a bunch of different things. And it's probably related to machine learning as well, now that I think about it. Because it's very, very similar. You're pretty much mapping using the graph or tree to map the relationship of space-time given two different points. Something to think about for later.
Really simple using this idea of two variables being shifted n-1 times. So as I said from the drawing explanation, we're going to have two variables, 1 and 2. Both are going to be initialized as 1, and then we're just going to loop through n-1 times. So for I in range n-1, and we're going to continuously update these two variables 1 and 2. So the first thing I'm going to do is update 1. 1 is going to be set to 1 plus 2, right? Because we're just adding the two previous values and then getting the new result. So 1 is being updated, and we would also want to shift 2 to whatever the previous value of 1 was. But you can see that we're updating 1 before we actually shift 2. So what we're actually going to do is store 1 in a temporary variable before we actually update it, and then we're going to set 2 to the temporary variable so that we don't end up setting it to 1 plus 2. We just want it to be set to 1, so we're going to set 2 equal to temp. Once this loop goes through n-1 times, we're going to end up just returning whatever 1 happens to land on, and that is the entire solution. We went through so much headache just to get to these 5 lines.
Yeah, I wonder what happens if you... Because I think there's probably a way to mix two different recursions together. If you imagine two trees or two graphs intersecting with each other, I wonder if there's a way to do that. And because that would be probably related to overfitting or underfitting in machine learning, I suspect. Because maybe you can find the connection between data points by trying to map out the intersection of these different recursion methods. So for example, Fibonacci moves at a center frequency like he explains here, and then maybe you can find a different pattern with a different flow of if-else statements, and then you can create another function that figures out the intersection of these two different recursion methods. And that can give you a relationship between data points that may be connected. Yeah, but first I have to get the stuff down to think about that. And it's a lot simpler the way that he did this than the way that he didn't even use recursion. But I'm definitely positive that because I know Fibonacci, you can use recursion, and it is a recursive pattern in nature, which all fractals are pretty much. And multifractals should be the intersection of different fractal patterns, which that's why I was thinking about trying to mix different recursion methods to figure out a method to draw a correlation between data points that might be more efficient than just using gradient descent or something like that. Or you can combine both, maybe. So he's looping from the bottom to the from the top to the bottom. It starts at the end and decreases, and 1 temp 1, then 1 equals 1 plus 2, and 2 equals temp. So it's passing the value of 1 to modifying the value of 1 each time and changing the 2, and then returns 1. Yeah, I'll have to think about this, but I think I'm gonna take a break now. How's rubber? Let's see, 49. Yeah, I'll take a break now, and then I'll try to get to 55 next time that I come. So see you then.